Hello everyone. Today our topic is stationary process from the chapter Random Process and Temporal Characteristics. The basic definition of stationary process. A stationary process in statistics and signal processing is a type of stochastic process whose statistical properties do not change over time. In simple terms, a process is called stationary if its mean, variance, and autocorrelation remains constant over any time. A stochastic process is said to be stationary if the joint statistical distribution of the same as that for all time shifts and for all the processes look like the same at any time. Its average value like mean and spread like variance do not change over time. The relationship between values like correlation depends only on the time difference, not on the actual time. A random process is also known as a stochastic process. X of t is said to be stationary if its statistical characteristics remain constant over any time. This means the probability distribution and various statistical parameters does not depend upon the time origin. This is the simple definition of the stationary process. Here we have discussed many types of stationary process: first order, second order, wide sense stationary, joint state stationary, like some other stationary processes. First, in stationary process, there are two orders. First order stationary process and second order stationary process. First order stationary process. A random process is said to be stationary to order 1 or first order stationary if its first order probability density function does not change with time or any with shift in time. If x of t is first order stationary process, then fx of xi semicolon t1 equals to fx of xi semicolon t1 plus delta t. Here delta t is the changed time for any time t1 where delta t is the shift in time. This means the probability density function fx of xi semicolon t1 is independent of actual time instant t1. Therefore, the mean value of the process remains constant with time. Hence, for a first order stationary random process, the mean value must remain constant. E of x of t is equals to x bar is equals to constant. Here, E of x of t is known as mean. The mean of first order stationary process must be constant. Proof. Proof for the first order stationary process. Consider a random process x of t with random variable x1 is equals to x of t1 and x2 of t2 at a time instant t1 and t2 is equals to t1 plus delta t respectively. This mean values are E of x1 is equals to E of x1 of t1 is equals to integral of minus infinity to infinity x1 fx of x1 semicolon t1 of dx1. E of x2 is equals to E of x of t2 is equals to integral minus infinity to infinity x1 fx of x1 semicolon t2 dx1. Now substitute t2 is equals to t1 plus delta t. E of x of t1 plus delta t is equals to integral minus infinity to infinity x1 fx of x1 semicolon t1 plus delta t of dx1. For a stationary random process, we know fx of x1 semicolon t1 plus delta t is equals to fx of x1 semicolon t1. Therefore, E of x of t1 plus delta t is equals to integral minus infinity to infinity x1 fx of x1 semicolon t1 dx1. The final we have to prove that E of x of t1 is equals to constant. Hence that the first order stationary random process, the mean remains constant with respect to time. Second order stationary process. A random process is said to be second order stationary process or second order stationary if the second order joint probability density does not change with respect to time or with any shift in time. In simple terms, if we shift the time axis, The joint density function of the random variable at two time instants remains the same. Mathematically, fx of x1 comma x2 semicolon t1 comma t2 is equals to fx of x1 comma x2 semicolon t1 plus delta t comma t2 plus delta t. For all t1, t2 and delta t, this means the function depends only on the time difference t2 minus t1 and do not on the actual time instants t1 or t2. Note that every second order stationary process is also a first order stationary process because distribution does not change with the time. Then the individual distribution also remains unchanged. Condition for the second order stationary process. For a process to be second order stationary, its autocorrelation function should be depend only on the time difference between two instants and do not on the absolute time. Let x1 and x2 be the random variables of random process x of t and time instants t1 and t2 respectively. The autocorrelation function is given by Rx of t1 comma t2 is equals to E of x of t1 x of t2. If we define tau is equals to t2 minus t1, then Rx of t1 comma t1 plus tau is equals to E of x of t1 plus tau is equals to Rx of tau. This means Rx of tau depends only on the time difference tau and it is independent of time. The another stationary process is White-Sense stationary process WSS. If a random process x of t is second order stationary, if it is called a White-Sense stationary WSS process or a weak-sense stationary process. However, the reverse is not necessarily true. A WSS process may not always be fully second order stationary. The conditions for a process to be White-Sense stationary are the mean of the process is constant with time. E of x of t is equals to x bar is equals to constant. The autocorrelation function depends only on the time difference tau and not on the absolute time t. E of x of t plus tau is equals to Rx of tau. Thus, the WSS process, both the mean and the autocorrelation remains the same regardless. Joint White-Sense stationary process. Consider two random processes x of t and y of t. If there are joint White-Sense stationary, their cross correlation functions depends only on the time difference between two time instants and not only absolute time. The cross correlation function between x of t and y of t is defined as Rxy of t1 comma t2 is equals to E of x of t1 y of t2. If we let tau is equals to t2 minus t1 and t2 is equals to t1 plus tau, then Rxy of t1 comma t1 plus tau is equals to E of x of t1 y of t1 plus tau. Here Rxy is cross correlation of tau. This means Rxy of tau depends only on the time difference tau. The conditions for two processes to be joint wide stationary are E of x of t is equals to constant, E of y of t is equals to y bar is equals to constant, E of x of t y of t plus tau is equals to Rx y of tau, which is independent of absolute time t. A random process x of t is said to be strict sense stationary if its nth order joint density function does not change with time or with shift of time value. Explanation. The statistical properties of x of t and n time points remains the same regardless of when we observe or if we shift by delta t. Examples, x of t1 and x of t2 behaves like x of t1 plus delta t and x of t2 plus delta t. Equation. Fx of t1 and so on x of tn, x1 and so on xn semicolon t1 comma and so on tn is equals to fx of t1 plus delta t bracket comma and so on x of tn plus delta t, x1 and so on xn semicolon t1 plus delta t comma and so on tn plus delta t. A process that is stationary to all orders of n is equals to 1, 2 and so on n is called a strict stationary process. Explanation. This occurs when the process maintains time invariance for all orders. Statistical movements are constant over time. Thank you.